A volumetric display device is a graphic display device that forms a visual representation of an object in three physical dimensions, as opposed to the planar image of traditional screens that simulate depth through a number of different visual effects. One definition offered by pioneers in the field is that volumetric displays create 3D imagery via the emission, scattering, or relaying of illumination from well-defined regions in space. Though there is no consensus among researchers in the field, it may be reasonable to admit holographic and highly multi-view displays to the volumetric display family if they do a reasonable job of projecting the three-dimensional light field within a volume. Most, if not all, volumetric 3D displays are either autostereoscopic or automultiscopic, that is, they create 3D imagery visible to the unaided eye. Note that some display technologists reserve the term autostereoscopic for flat-panel spatially multiplexed parallax displays, such as lenticular sheet displays. However, nearly all 3D displays other than those requiring headwear, e.g., stereo goggles and stereo head-mounted displays, are autostereoscopic. Therefore, a very broad group of display architectures are properly deemed autostereoscopic. Volumetric 3D displays embody just one family of 3D displays in general. Other types of 3D displays are stereograms, stereoscopes, view sequential displays, electro-holographic displays, parallax, two-view displays and parallax panoramograms, re-imaging systems, and others. Although first postulated in 1912, and a staple of science fiction, volumetric displays are still under development, and have yet to reach the general population. With a variety of systems proposed and in use in small quantities, mostly in academia and various research labs, volumetric displays remain accessible only to academics, corporations, and the military. Types. Many different attempts have been made to produce volumetric imaging devices. There is no officially accepted taxonomy of the variety of volumetric displays, an issue which is complicated by the many permutations of their characteristics. For example, illumination within a volumetric display can either reach the eye directly from the source or via an intermediate surface such as a mirror or glass. Likewise, this surface, which need not be tangible, can undergo motion such as oscillation or rotation. One categorization is as follows. Swept volume display. Swept surface volumetric 3D displays rely on the human persistence of vision to fuse a series of slices of the 3D object into a single 3D image. A variety of swept volume displays have been created. For example, the 3D scene is computationally decomposed into a series of slices, which can be rectangular, disc-shaped, or helical cross-sectioned, whereupon they are projected onto or from a display surface undergoing motion. The image on the 2D surface changes as the surface moves or rotates. Due to the persistence of vision, humans perceive a continuous volume of light. The display surface can be reflective, transmissive, or a combination of both. Another type of 3D display which is a candidate member of the class of swept volume 3D displays is the varifocal mirror architecture. One of the first references to this type of system is from 1966, in which a vibrating mirrored drumhead reflects a series of patterns from a high frame rate 2D image source, such as a vector display, to a corresponding set of depth surfaces. Static volume. So-called static volume, volumetric 3D displays create imagery without any macroscopic moving parts in the image volume. It is unclear if the rest of the system must remain stationary for membership in this display class to be viable. This is probably the most direct form of volumetric display. In the simplest case, an addressable volume of space is created out of active elements that are transparent in the off state but are either opaque or luminous in the on state. When the elements are activated, they show a solid pattern within the space of the display. Several static volumetric 3D displays use laser light to encourage visible radiation in a solid, liquid, or gas. For example, some researchers have relied on two-step-up conversion within a rare earth-doped material when illuminated by intersecting infrared laser beams of the appropriate frequencies. Recent advances have focused on non-tangible implementations of the static volume category, which might eventually allow direct interaction with the display. For instance, a fog display using multiple projectors can render a 3D image in a volume of space, resulting in a static volumetric display. A technique presented in 2006 does away with the display medium altogether, using a focused pulsed infrared laser to create balls of glowing plasma at the focal point in normal air. The focal point is directed by two moving mirrors and a sliding lens, allowing it to draw shapes in the air. Each pulse creates a popping sound, so the device crackles as it runs. Currently it can generate dots anywhere within a cubic meter. It is thought that the device could be scaled up to any size, allowing for 3D images to be generated in the sky. Later modifications such as the use of a neon, argon, xenon, helium gas mix similar to a plasma globe and a rapid gas recycling system employing a hood and vacuum pumps could allow this technology to achieve two-color and possibly RGB by changing the pulse width and intensity of each pulse to tune the emission spectra of the luminous plasma body. Human-computer interfaces. The unique properties of volumetric displays, which may include 360-degree viewing, agreement of converge and accommodation cues, and their inherent three-dimensionality, enable new user interface techniques. There is recent work investigating the speed and accuracy benefits of volumetric displays, new graphical user interfaces, and medical applications enhanced by volumetric displays. Also, software platforms exist which deliver native and legacy 2D and 3D content to volumetric displays. Artistic use. An art form called Hologlyphics has been explored since 1994, combining elements of holography, music, video synthesis, visionary film, sculpture and improvisation. Volumetric movies have been shown to live audiences at film festivals, art galleries and music events. Multiple volumetric displays and multi-loudspeaker arrays surround an audience. The movies are shown in conjunction with music, either live or recorded with the volumetric animations. The original intent was to combine holography with music, and finally volumetric displays were settled on as an artistic medium. Many traditional film and video special effects have been adapted to hologlyphic movies. Plus many more special effects unique to volumetric displays have been developed. These include volumetric wipe effects, raster bending, morphing, kaleidoscope and mirroring effects, experimental rotations, spatial warping effects and image sequencing. The hologlyphic movies can also be performed in real time, like a video synthesizer, controlled by musical keyboards, motion sensors, control panels, and acoustic instruments. The image generation system is mostly digital, but some of the original image generators and processes were analog and remain in use. Drawbacks. Known volumetric display technologies also have several drawbacks that are exhibited depending on trade-offs chosen by the system designer. It is often claimed that volumetric displays are incapable of reconstructing scenes with viewer position-dependent effects, such as occlusion and opacity. This is a misconception. A display whose voxels have non-isotropic radiation profiles are indeed able to depict position-dependent effects. To date, occlusion-capable volumetric displays require two conditions. The imagery is rendered and projected as a series of views, rather than slices, and the time-varying image surface is not a uniform diffuser. For example, researchers have demonstrated spinning screen volumetric displays with reflective or vertically diffuse screens whose imagery exhibits occlusion and opacity. One system created HPO 3D imagery with a 360-degree field of view by oblique projection onto a vertical diffuser. Another projects 24 views onto a rotating controlled diffusion surface, and another provides 12 view images utilizing a vertically oriented louver. So far, the ability to reconstruct scenes with occlusion and other position-dependent effects have been at the expense of vertical parallax, in that the 3D scene appears distorted if viewed from locations other than those the scene was generated for. One other consideration is the very large amount of bandwidth required to feed imagery to a volumetric display. For example, a standard 24 bits per pixel, 1024 x 768 resolution, flat 2D display requires about 135 megabytes per second to be sent to the display hardware to sustain 60 frames per second, whereas a 24 bits per voxel, 1024 x 768 x 1024 volumetric display would need to send about 3 orders of magnitude more to the display hardware to sustain 60 volumes per second. As with regular 2D video, one could reduce the bandwidth needed by simply sending fewer volumes per second and letting the display hardware repeat frames in the interim, or by sending only enough data to affect those areas of the display that need to be updated, as is the case in modern lossy compression video formats such as MPEG. Furthermore, a 3D volumetric display would require 2 to 3 orders of magnitude more CPU and/or GPU power beyond that necessary for 2D imagery of equivalent quality, due at least in part to the sheer amount of data that must be created and sent to the display hardware. However, if only the outer surface of the volume is visible, the number of voxels required would be of the same order as the number of pixels on a conventional display. This would only be the case if the voxels do not have alpha or transparency values. Market. Currently there are a handful of companies involved in development of 3D volumetric display technologies. These include 3D Icon, Felix 3D, Holographica, Holoverse, Lightspace Technologies, Sosho Bolograph, VOXON, and Zebra Imaging.